Do you have any question from previous parts? Okay, so let's start. We have one remaining example from previous parts, and today we start to solve this, and then we start the next concepts for this week. Okay, here we have this structure. The end A of the uniform 5 kilogram bar is pinned freely to the collar. So here, this connection at point A is a pin connection, which has an acceleration of 4 meters per second square. So this acceleration A is 4 meters per second square along the fixed horizontal shaft. So it's moving to the right side direction. With acceleration 4. And if the bar has a clockwise angular velocity of 2 radian per second, this is the angular velocity of the bar as it swings past the vertical, determine the components of the force on the bar at A for this instant. So we have a system consists of a bar and a slider. The slider is moving to the right with acceleration A, which is known for us, and this is 4 meters per second square. This bar is connected to the slider with a pin connection. At the same time, this bar is rotating about pin A with angular velocity omega, which is 2 radian per second. So we know how much is this. And we want to obtain the reaction force at this pin A when the bar passing the vertical position as shown here, you can see. So for this purpose, if you plot the free body diagram for this bar, we will have two reactions at point A. And at this time, the normal reaction is clearly equal to the weight of this bar. But to obtain the horizontal component, let me plot the reactions. At this point A, we will have two reactions. One is, if we call it AX, which is the horizontal component, and the other one is AY, which is the vertical component. The AY is clearly equal to the weight of this bar because there is no motion in vertical direction. Yes, so we can find AY clearly, easily, but AX, this term, if you write the force equation in X direction, since this bar is moving in a horizontal direction and it has an acceleration, it's not easy to obtain AX. Of course, for AY, we have the same scenario, yes, because this bar is rotating. If we assume this is the mass center of this bar, it has acceleration in X and Y. So for AX and AY, if we write the force equation in both direction, in the right hand side, we have acceleration. So we cannot easily obtain AX and AY. And for this purpose, we need to obtain the acceleration of this point, the mass center. When we obtain the acceleration for the mass center, then we can find AX and AY from the equation of motion for this bar. So the first step, we need to obtain the acceleration for this center. And to obtain the acceleration for the mass center, we need to the equations of kinematics from the previous chapter. And we can use, as you can see here, we use the equation of relative acceleration. And here we have a rotating coordinate system. So we can write the acceleration of the mass center point G. This G is the mass center of the bar. So we can write the mass center acceleration for this point in terms of the acceleration of point A. So AG is equal to the acceleration of A plus the angular acceleration cross R. This alpha is the angular acceleration of this bar, because we don't know how much is this. We just know that the angular velocity is 2 radian per second, this term, but we don't have any information about the acceleration of this bar. R is the position vector of point G with respect to point A. Omega is the angular velocity of this bar, which we know it's 2 radian per second. And the term of 2 times by omega across V relative, because A and G are located on a rigid body and there is no motion between these 2 points, and the relative velocity between point A and G is equal to 0. So we neglect that term. And this is the equation for the relative acceleration between point G and point A. Now we can substitute our given data. We know that the acceleration of A is 4I, because A is located on this slider. So it has a pure translational motion. As you can see, this is 4 meters per second squared, the acceleration for this point. Alpha, we assume that alpha is in the direction of omega. So in vector form, it will be minus alpha k, because you can see here, based on this coordinate system, x and y, the direction of omega in vector form is minus omega k. And for alpha, if we assume that alpha is again in the same direction and it's in clockwise direction, so alpha will be minus alpha k. Omega is equal to minus 2k in vector form, as I told you. And R, which is the position vector of point G with respect to point A. If you put this coordinate system, if you move it to the point A here and put it here, the position vector of point G is minus 0.4j, because G is at the center of the bar. The total length of the bar is 0.8. So 0.8 divided by 2 will be the position of the mass center, and it's equal to minus 0.4j, because it's in vertical direction. So now we can substitute this given data in the equation for AG, and we can obtain that AG is equal to this term. We will have, this is the acceleration of point A. This is the unknown angular acceleration for the bar. This is the R. This is omega, and finally again R. Now we can substitute this term. Here we have K cross J. K cross J is minus I. K cross I, which is J. Okay. Again, here we have K cross J, which is minus I. So we can substitute and simplify. And finally, we will have the acceleration of mass center. You can see the mass center has the acceleration in vertical and horizontal direction. In the vertical direction, the acceleration is clear, is 1.6. In fact, this acceleration is R omega squared. And because we know how much is R and omega, so we know the acceleration in vertical direction for the mass center. So easily from this term, you can obtain AY. But if you want to obtain AX, we need to obtain alpha, because this alpha is again another unknown. So we cannot obtain AX directly from this equation. We still need another extra equation to obtain alpha. Okay. Any questions so far? Is it clear? Okay. So from the kinematics, we obtain the acceleration of the mass center of the bar in terms of the acceleration of point A, and we obtained this term for the acceleration of the bar. Okay, so the next step, we can use the kinetics equation. In the kinetics, we can write the force equation and also the moment equation about any other point. So we write the force equation in x and y direction, and we wrote the moment equation about the mass center. As you can see, the moment equation about the mass center, it means about this point. This is the mass center. If you write the moment equation about this mass center, we have two reactions, AX and AY here. Yes, AY will pass through this point. So the moment due to the AY, or the vertical component of the reaction at A, is equal to 0. But AX will create some moment, and its moment is equal to AX times by its arm, which the arm is this length, is 0.8 divided by 2. So this is the moment due to AX. And also we have the weight of the bar, which the weight again is located on the mass center, so it doesn't have any moment about point G. So if you write the moment about G, we will have only AX times by its arm, which is L divided by 2, or 0.8 divided by 2. So this is the moment about G. It must be equal to IG alpha, which IG is the mass moment of inertia about the mass center, and alpha is the angular acceleration. So we can substitute IG, which is for a bar, we know that is equal to 1 divided by 12 times by ml squared, and times by alpha, which is the angular acceleration. So this is another extra equation that I told you we needed to obtain the alpha and AX. So now we know that the relation between AX and alpha. So if you write the force equation in X direction, as you can see here in the first equation, we have the force equation in X direction. Again, we only have AX. In the free body diagram for the bar, we only have AX, and it's equal to the mass of the bar times by the acceleration in X direction. The acceleration in X direction is this term, the I component. So AX is equal to m times by 4 minus 0.4 times by alpha. So here we have two equations. One is this equation and the other one is this. From these two equations, you can solve and obtain AX and alpha. Okay, so we have two equations with two unknowns. To solve this equation easily, you can substitute here in this equation, instead of this AX, you can substitute from this term 0.133 m times by alpha. It's equal to m times by 4 minus 0.4 times by alpha. The m will be cancelled out, and you can easily obtain that alpha is equal to 7.5. This is the equation. And by solving this equation, you can easily obtain the alpha. And then you can substitute alpha here in this equation. Alpha is equal to 7.5, as you can see here. You can obtain AX. And to obtain the normal or vertical components of reaction force at point A, easily you can write the force equation in y direction, as you can see here. In the y direction, we will have AY, the reaction at point A, and also we have the weight of the bar. So AY minus mg is equal to the acceleration in y direction times by m, which the acceleration in y direction is the j component, is equal to 1.6. And easily you can obtain that AY is equal to 11.4 times by m, which m in all of these equations are the mass of this bar. And I think we don't have the value for this. Let me, yes, we have the weight, it's equal to 5 kilograms. So you can substitute m is equal to 5, and easily you can calculate all of these results. I mean, AY is equal to 11.4 times by 5, alpha is equal to 7.5, it's clear, but for AX is equal to 0.99 times by 5 because we have the mass is equal to 5. Okay, any question from this example or from the previous examples? If you have any questions, please ask. Otherwise, I will start the next part of this chapter. Okay. Okay. We continue with the plane kinetics of rigid bodies. In this section, we will study the work and energy equation, and the power in rigid bodies motion. So the first step, we need to know what is the advantages of the work energy method. It's similar to the particles when we discussed the work and energy methods in particles. I explained that what is the benefit of this method. And now again in the rigid bodies, we have again the same benefits. Can you tell me what is the advantage of the work energy method in rigid bodies or particles? No different. Any suggestion? Yes, your answer is to somehow correct. In fact, when we use the work energy method, thank you for your answer. When we use this work and energy methods, in this method, in fact, we do not consider the past as you told, and we neglect the determining the acceleration. Most of the time, when you use the Newton's second law, the first step similar to the previous example in previous section, you see that we need to obtain the acceleration, and then using the acceleration, we find the reaction forces. But if you use work and energy methods, you don't need to obtain the acceleration, and without calculation for the acceleration, I mean, when I say acceleration, I mean the linear and the angular acceleration, both of them. We don't need to the kinematics relations for the acceleration. You can easily find the reaction force by using these equations, work and energy. And then you can integrate over your interval to obtain the velocities. So we don't need to find the acceleration to obtain the velocities and displacement, and finally to obtain the reaction force. Sorry, but you can easily find the reactions and the forces using these work and energy equations. The procedure is exactly similar to the particles. I mean, there is no different here. Just the difference between the particles and rigid bodies is how to calculate the kinetic energy and potential energy. The potential energy is usually is the same because you calculate based on the mass center of your rigid body, but the kinetic energy, it will be a little different, and I will explain what's the difference. Because in the rigid bodies, in addition to the translational motion, we have rotational motion. In the particles, when we have a particle, there is no dimensions for a particle, so it only can have a translational motion. In the translational motion, the kinetic energy is equal to half mv squared. Yes, but in the rigid body, in addition to the linear velocity, which is v, we have the angular velocity omega. So the kinetic energy will be changed a little, of course, when we have rotation, and we will discuss in the next slides, and you will see the general procedure to solve is the same. But before that, we need to obtain the work done by external forces and external moments. For the external forces in a rigid body, we usually prefer to use the vector form because we have dimensions. The direction of the force and direction of the motion is very important. And sometimes it will be complicated to use the scalar method. So we usually prefer to use the vector form. In the vector form, if you want to obtain the work done by force F, this is the external force F, the equation is the same. It's the integral of F dot dr. This is the dot product, and dr, which is in fact the displacement vector. So if we write it, if we open this dot product, you know that F dot dr is equal to F cosine alpha ds, which ds is in fact the amplitude of the vector dr. Alpha or cosine alpha is the angle between F and the vector dr. Okay, so always this is a general equation in mathematics. I mean, the A dot B is equal to A B cosine alpha, which A B is the magnitude of the vectors. And this F is again the amplitude of vector F. Okay, so this is the scalar form of the equation F dot dr. Also, if we have a couples, external couples, it will do some work on your system, and it's equal to m d theta. Okay, and it's similar to the particles. But about the kinetic energy, as I told you, we have different forms for the kinetic energy in the rigid bodies. First one is the translational motion. I mean, when we have translational motion, to calculate the kinetic energy, the kinetic energy is directly to the motion. When we have motion, we have kinetic energy. We divided the motion in the rigid bodies into three main categories. If you remember, the first category was the translational motion. The second one was the pure rotational motion. And the third one was the general plane motion. Yes, it means that we have rotation and translation at the same time. The first case is translational motion. In the translational motion, you can see this rigid body is translating and with a velocity v. This v is the velocity for each point. I mean, here, if you assume this is the mi, which is one point on this rigid body, the velocity of this point is again equal to v. So v is, or v bar, here we show with v bar. This v bar or v is the velocity of each point on this rigid body, because this is a translational motion. So the velocity of each point on this rigid body is equal to v or v bar. And the kinetic energy for this rigid body is half times by mv squared. It's exactly similar to the particles. So when we have translational motion in a rigid body, the kinetic energy is exactly the same term in a particle. as the particles, and it's equal to half mv squared. And m is the mass, the total mass of this rigid body. So you can see the first case is similar to the particles, but the second case, when we have a pure rotational motion or fixed axis rotation, in this case, there is no translational motion, and this rigid body, as you can see, is rotating about point O, about this point. So there is no translation, there is no linear velocity, v, and here we have only one angular velocity, omega, as you can see. The velocity of each point in this case is related to omega and its position with respect to point O. For example, this point mi, if we call it point I, the velocity of this point is equal to its radius with respect to point O, ri, times by the omega angular velocity. The omega, if it was constant, but vi is not constant, because vi is equal to ri times by omega. I mean, the velocity of this point, for example, is not equal to the velocity of vi, okay? But the kinetic energy for this rigid body is equal to half times by mass moment of inertia times by angular velocity squared. As you can see, there is no linear velocity in this term. And this IO, this is very important. This IO is, is the mass moment of inertia about this point O. Okay, so IO is the mass moment of inertia about this point. It's not about the mass center. It's very important. You should consider when you are calculating the mass moment of inertia, this mass moment of inertia in this equation is not about the mass center. You need to calculate this about the fixed point that you are calculating. You have the rotational motion. So this is the IO, and omega, as I told you, is the angular velocity for the rigid body. Okay, so this is the second case. And finally, the last one, which is the general plane motion. In this case, this rigid body has translational and rotational motion at the same time. It can rotate and translate at the same time. So the kinetic energy for this body, as you can see, includes the linear velocity and angular velocity as well. So because its mass center at the same time has some velocity and some angular velocity. The general form for this body to obtain the kinetic energy is equal to half mv bar squared, which v bar is the velocity of the mass center. It's very important. This time, the velocity of each point is not v bar. As you can see, this is mi. The velocity of mi, in fact, is vi. It's not equal to v bar, because this body is rotating and translating, okay? So due to the rotation, the velocity of point mi is not equal to the velocity of the mass center g. But in the kinetic energy, you should consider the velocity of the mass center, which is v bar. So to obtain the kinetic energy for a rigid body, we need to obtain the velocity of the mass center. Clear? So this is, in this equation, this is half mv bar squared plus, and this is the kinetic energy due to the rotation. It's equal to half mass moment of inertia omega squared. And here, this mass moment of inertia this time is about the mass center, okay? So I bar is the mass moment of inertia about point G, or about the mass center, okay? So it's not the same in the previous equation. And omega is the angular velocity of the rigid body, which is clear. This is because this body is rotating with this angular velocity, okay? Any question from these three types of kinetic energy? Is it clear? Any question? Okay. Here we have one point. For the general plane motion, we also can write the kinetic energy in this term. You can see half IC omega s squared, which IC or point C, here this IC in fact is this term, IC, is the mass moment of inertia about the instantaneous center of zero velocity, and C is the instantaneous center of zero velocity. This equation is very useful when we can find the instantaneous center of zero velocity and it's clear for us. I mean, in some examples, you don't need to plot that lines and you don't need to the geometrical method to find the instantaneous center of zero velocity. And easily you know that which point is your instantaneous center of zero velocity. So to obtain the kinetic energy, you can directly write this equation and you can find the mass moment of inertia about this point, and then you can find your results. But the best here you can see what is an example for C that we don't need to use the geometrical method. I mean, the very popular method, the popular example that we know what is the instantaneous center of zero velocity. Do you have any idea for this one? Can you tell me one example? In the previous session, we solved one example about this, and I explained. When I started the general plane motion, I told you one example, and in that example, I explained that one of the most popular of the motion, which we know directly that where is the instantaneous center of zero velocity. Can you tell me, do you remember? No idea? If you remember, in the motion of the wheel, the motion of a wheel on the surface, we have two cases. If you remember, the first case was the rotating without slipping, and the second one was rotating with slipping. You remember? In that case, when we don't have a slipping, the connection point between the wheel and the surface, in fact, is the instantaneous center of zero velocity. And you can assume that if I told you this exactly the same sentences in last week, I told you when the wheel is rotating without slipping, we can assume that the connection point between the wheel and the surface is your instantaneous center of zero velocity. And you can assume that the wheel is rotating about that connection point. So in this type of problems, when we have rotation without slipping, we can assume that the mass center, the instantaneous center of zero velocity is the connection point, and we call it C. And to obtain the kinetic energy, you can use this equation, half IC omega squared. It's very useful and will decrease your calculation in the examples. So anytime in each equation, in each problem, if you know that what is the location of the instantaneous center of zero velocity, and you want to use the, if you want to use this work and energy equation, it's better to use this equation. Okay. So this is the work energy equation in a rigid body. You can see it's similar to the particles. We have kinetic energy in the initial position, potential energy in initial position. W1 to 2 is the work done by the external forces other than the weight and spring force. The weight and spring force will considered here in this V sub 1 and V sub 2, okay? And T sub 2 is the kinetic energy in final position, and V sub 2 the potential energy in final position. As I told you, the weight will be considered in this term in V. We had one question in the assignment 1. In the first question in the assignment 1, we had, most of you used the work and energy equation to obtain the velocity of that mass before the impact to the ball. To obtain the velocity, you use the work and energy equation, but you neglected the, here, you neglected the weight and this term V. And most of you made the same mistakes, and you neglected the potential and gravity potential energy in this equation. So this V includes the gravity potential energy, the position of the mass center and the rigid body. And also, if you have the one spring in your system, this V includes the potential energy stored in the spring. Okay, and T is the kinetic energy. We know how to calculate the kinetic energy for a rigid body, and W is obtained from that vector form that I explained in previous slides. Okay, so no question from this part. Okay, the last concept in this section is the power. And you know that power is equal to, okay, thank you. The power is equal to F dot V. Again, this is in vector form. As you can see, F is a vector, V is vector, and M omega is the moment times by the angular velocity. Our time is almost finished, and in less than 1 minute, because I have time restriction, so in less than 1 minute it will be finished. So if you don't have any question, we can wrap up this session, and I continue this concept tomorrow because it will be interrupted by the software because of the time restrictions. Any question from this part? No question?